Good morning, everybody. Welcome back. It's your third day of DConf. It's not the last day, but it's the last day of talks that we're going to be having. And the fourth day on Sunday, if you're attending, is a hackathon, which I've made reference to throughout the last 2 days. So I'm being told the live stream is up, so good morning or good evening or good any time of day or night to everybody on the live stream. And hopefully all of you had time for some breakfast here and got some coffee. We're going to kick off today with this man that, I don't know if people know who this is.
It looks like not.
Mr. DIP, right? So yeah, give a round of applause for Andrei's keynote.
Good morning. So I was 8 years old, and my parents took me to the beach on vacation. And you know, kids like walk on the beach and kind of they look at things on the in the sand. And I found a crumpled piece of paper. I picked it up, I unfolded it. It was 50 Deutschmark. Remember the Deutschmark? All right, during the Cold War, the Bundesrepublik's hard currency. It was amazing money even for an adult in Romania at the time. So I said, Dad, look, I found 50 Deutschmark. I said, oh, you're a lucky boy, good for you. Keep it for later, for college or whatever. And oddly enough, the next day we walk in a completely different part of that tourist place, and I find another crumpled piece of paper. And I pick it up, I unfold it, and it was 50 Deutschmark. I said, Dad, I found another 50 Deutschmark. And Pop said, kid, where did you steal all that money from? That's why I learned my lesson that two remarkable coincidences in a row are, breed suspicion. So it's kind of a difficult charge, a difficult thing to come to someone with, to say, I found, I won the lottery twice. Actually, I just read this article about a guy who won the lottery twice, and then he said he has a system, and he's selling the system for winning the lottery. And apparently it's some sort of XOR kind of thing among the previous winner numbers, and you do some formula, and you get the next winning number, which is pretty awesome if you think of it. It's $175. You can come to me after this. All right. So I am equally apprehensive today to talk about this, design by introspection, which is one of those remarkable coincidences that I seem to have stumbled upon. So by means of history, let's recap design patterns. Who knows about design patterns? They should be indeed, thank you very much, in the vocabulary of all of us. So they've been inspired by Christopher Alexander's physical architecture work. And they're reusable solutions to problems that come again and again and again in our programs, in our systems. And they've had a huge heyday in the early 2000s. Most of us probably remember those days. There was a conference, there were books, there were like a lot of stuff. But then there's been too much of it, and then people the pendulum swung back, and people are like, we're sick of it, and so on and so forth. But definitely they have left a lasting influence on design methodologies. Now, narrowing the domain a bit, we're looking at policy-based design, which was coined by Modern C++ Design, the book. And it was some sort of let's implement the patterns kind of thing, which was a preposterous thing to even talk about. But in the end, it kind of became successful. So much so, in fact, that it is one of the 76 programming paradigms listed in Wikipedia's Hall of Fame of Programming Paradigms. Now, there's something interesting about this. So programming paradigms which be like functional, procedural, what have you, declarative, etc. And there's 76 listed. They have there's a little hierarchy and there's indentation and whatnot. And among those, there's policy-based design. It has been successfully used in C++ and D. And well, I coined that thing. So that's my first 50 Deutschmark. Oh, no, thank you. Thank you. Scattered golf applause, okay? Yeah, thank you very much, yeah. All right, so I got lucky with this. I didn't invent the thing as much as popularize it and give it a name and use it consistently. So there's an interesting relationship between the two, design patterns being the larger way of looking at things, and policy-based design being a much more specific and specific both to the domain and the language thing. They both, however, approach the same fundamental issue. You have similar designs in response to similar problems. So in patterns, the programmer knows the pattern, like I'm going to do a factory right now. Actually, I'm going to, no, wait a second, I'm going to do an abstract factory, or whatever, right? And they sit down and write the code, and they put in a comment, for example, in the name of the types and everything. This is a factor, and this is a visitor, this is an observer kind of thing. And in policy-based design, the remarkable thing is, you take a look at the number of these artifacts that people produce for design patterns, and you say, oh, there's quite a bit of commonality in there. And guess what? We have this template engine lying at our feet. So we can use it as a sort of a macro preprocessor that generates a bunch of code for us from some predefined patterns. So far, so good? Thank you. To wit, Mark Dominus, a prominent member of the community, he made this very interesting remark, which is the design pattern solution is to turn the programmer into a fancy macro processor. If you this and you're kind of a guy like us, you think, wait a minute, fancy macro processor, I can do this. I could do an actual fancy macro processor, not a human macro processor, right? So in policy-based design, you go by mixing such little components during compilation, and there's really nothing new. It's pretty much interface-based programming, or even it's a pattern, the template method pattern. Now, compiled static assembly is nice. It's nicer than traditional interface-based design because there's little friction between components there. The layout is simpler. There's no indirection. The assembly is more direct. And everything is better type-checked. And you have a bunch of benefits from that. So this kind of semi-automated macro processing, if you search for policy-based design, you're going to find a number of designs that actually use it. And it goes with the following trade-offs. So you would have better reuse, obviously. You're going to have great static checking because everything is assembled sort of, in situ, right on the spot. You have good efficiency because there's no indirection, there's no dynamism, there's no runtime anything. It's all compile time. However, obviously, there's also a drawback in that they're runtime rigid. There's no dynamism. You can't do an interpreter kind of thing like that. There's no, you can't replace pointers to function. You can't replace interfaces dynamically and stuff like that. There's no graceful degradation. If you don't have the right components, you can't, you get compile time error. This is not supported. This method doesn't work. You're calling a method that doesn't exist, that kind of stuff. So there's no graceful degradation of designs with less capable components. And there's a lot of compile time dependencies because it's all this white box assembly that we're doing here. A simple example would be, I have a simple, it's almost as trivial as it gets. We have a structure, a class or whatnot, that is parameterized on a number of policies, and I'm going to store the policies within the object, and I'm going to use them relying on implicit interfaces. Nothing fantastic here. And actually, it leads to a much more interesting opportunity. So Richard Feynman, in a famous paper which launched the whole nanotechnology domain, said, he made a remark which goes the following way. He said, there's no breakage of any law of physics to be able to have very small mechanisms that assemble molecules in pretty much any way. The way we go about it, today is we have these chemical reactions and catalysts and whatnot, and we hope that the appropriate energies and whatever are in the right amounts, such that the reaction occurs and we get the new molecules in place. But that's, if you think of it, it's quite a ham-fisted approach. It's not very delicate. So then Feynman said, well, there's nothing contradictory in saying I want to assemble atoms by hand. It's just that my hands are too big, right? So similarly, what if we took this to code? I said, actually, I can assemble code by hand. And there are ways to make it like mold. As macro expansion is pretty dumb. It's just you have these macros and you expand and they explode in your face, and there's very rigid ways in which you can do all this macro assembly. But what if macros had kind of dendrites? They're kind of smart that way, and they adapt to one another. Like, oh, this macro with this macro, they kind of discover about each other. Oh, cool, so they make a covalent bond. I realize I'm saying a lot of ignorant things right now. But, anyhow. So they establish a connection that is possible because these macros understand each other. Do you have a free electron right there? Yeah, sure, here's an ion for you. That kind of stuff, right? So the core idea is then that instead of the programmer assembling mental patterns that have like 100% plasticity because they're in my mind, so they're not written yet, so I sit down and write them. And if I want to change anything, well, I change it from the way to my mental model all the way to the hands, right? So that would be one extreme. There's no code reuse because all the code is in my head, in my mind. But there's ultimate flexibility because I can write any variation of any pattern I want at any time. In policy-based design, actually the programmer assembles some rigid macros abiding to rigid interfaces, and to the extent you get it kind of assembled properly, it's going to work great. So there's no plasticity, but there's good code reuse. In design by introspection, you get in the middle of the road. You get some of both. You assemble, so you mold smart macros that communicate with and adapt to each other in ways that I'm going to show in a minute. And you get plasticity, but you also get code reuse. So this is the other 50 Deutschmark. And I actually think it's not 50, I think it's 50 million. Yes?
Where did you steal that money?
Sorry?
Where did you steal that money from?
Where did I steal that money from? Yes, let's see. Yes. Actually, I've been so apprehensive about this that I'll be honest, I've been working on this for months, probably a year. And I was thinking this is not believable. And today is really the first time I'm coming in the open and say, it's out of the closet. So, prerequisites for the language to be able to do design by introspection. And you got to have some input to design by introspection, which is introspection. And it goes the following way. You must be able to introspect types, such as what are methods, what are members, what are your things that you can do. What can you do? And all of this must occur. It's designed by introspection. It's not run by introspection. It's not, it's not implementation by, it's not execution by introspection. So this is not runtime introspection. We're talking about design. We're talking about assembling things. Everything occurs way before anything runs. So we have the ability to introspect types during compilation statically as a prerequisite. And the simple variant would be a query approach, which goes, do you support this particular method, primitive, whatnot. So then we have design by introspection processing. We need to evaluate during compilation a bunch of good stuff, the usual code. We need to be able to do arbitrary processing. We need to have a Turing-complete machine that is also highly usable to do processing of these designs. And we need to have output of these designs, such as generate any code we want. And these are the three tenets of design by introspection. You got to be able to do these in order to do design by introspection. So how does this stack up? Design by introspection input. Somebody, yes, Johan.
The compiler traits, for example?
Yes, tuple of traits, any number of STD traits or built-in traits or whatnot, mechanisms. You can have any compiles. I mean, when I say underscore traits, I include underscore trait compiles, which is a query. Would this code compile if I so much fancy as inserting it in my actual code? It's it's an amazing thing, because it's like you go to a policeman and say, if I go over 80 miles an hour on that road at that time, are you going to find me or not? Right? It's an interesting query to say, would this compile? It's a very interesting, if I kill you right now, would I go to jail? Oh, no, nobody would discover. Okay, let me kill you right now. So these are very good mechanisms for the D language to do design by introspection with. How about design by introspection processing? What do we have there? Thank you. Static if. We have compile time function evaluation, arbitrary expression execution. And we have static if, which is I give it a special place in here. I'm arrayifying it to some sort of a first-class citizen status, because I made an interesting discovery. Let me go. What the heck? Let me go forward just a bit and make the following extraordinary claim, which is each use of static if doubles the design space you may be covering. It's a fork in design space. Because what is if? Wow, it's getting really philosophical, doesn't it? What is if, ladies and gentlemen? What is if but a way to fork execution in time, like in real time? It's executing, and at some point, like, oh, if this is the case, I'm going to do that. Otherwise, I'm going to do something else or nothing, right? And that means I'm doubling the number of behaviors I'm doing during runtime. If you take that to the static domain, it's very interesting, because it means you're doubling the number of behaviors you're implementing, not doing. You're doubling the number of the real estate of the design space you're covering. So really, I want my design all to have like static if every 2 lines. That's a great design, because it just grows exponentially, covers everything. There's one design, and you want a browser, it's somewhere in there. You want a compiler, it's somewhere in there, because I'm covering so much space. So let me go back a bit now. And as far as DBA output goes, what do we have there in the D language? Output, mixin. So I have things like template expansion. It's a simple expansion of code. And we also have string mixin, which is the ultimate flexible engine for generating pretty much anything you want, right? So actually, I would say that these rather very well equipped for this kind of stuff. There are things we can do better, such as nicer way to loop through the members of a class, for example. We don't have that. We got to use recursion and stuff. But everything is doable and everything is there. So that's nice. OK, let me talk a bit about the first fundamental point of design by introspection, which is optional interfaces. And it goes like this. Design by introspection component typically prescribes a number of required primitives in a component. So you define a component and it says you must implement the following primitives. Empty front and pop front. Sound familiar? Right? So it must implement these required primitives, but it also has a number of optional primitives, which may be in any number. And the interesting thing is the actual component may implement any subset of those optional primitives. How many possible interfaces can I define? It's the power set. Yes, thank you. It's the power set. It's 2 to the power of NO. Right? The number of, sets, the number of distinct subsets of a set. Right? So in a very compact form, I like this because I hate writing code. All of the best code I write is like 50 lines or less. This is my benchmark. I don't want to write much code. I want to write very little code, but I want it to be executable. I want it to be highly reentrant, if you wish, from a design perspective. So we're covering an exponential space with a simple definition. And we have an interesting consequence to that, because we have a linear specification for exponential behaviors. And what's interesting here is that what's missing is as important as what's there. Because if an interface does not implement this particular primitive, it means that and they don't do that. And no information is information. The absence of a bit is a bit. Right? It's like, you see what I'm saying? And traditionally we go, oh, there's got to be all ones here. All of the bits here must be checked. If you don't check any boxes in this interface implementation, it's not valid. It doesn't compile or it doesn't run. It doesn't work because you forgot to implement this particular part of the interface. But no, I come and say, you know what? If there's no bit, there's a 0 in there, which is equally informative. So what's not there is as important as what's there. So then we have linear code for covering exponential behaviors, and that includes state variations too. You may define a data member or not. So the state is also very moldable. And we have no penalty for height-challenged interfaces, which are traditionally bad, right? People say, oh, if you define an interface that's too large, it's an anti-pattern. It's not a nice thing to do, right? But in this case, I can say I give you an interface of 100 primitives, but you choose what to implement. It's buffet. You go and choose all you can eat, right? You can implement all 100, but you can implement 0. And any subset you want, exponential, right? Okay. So there's no penalty for large specifications. And there is also some sort of interesting graceful degradation going on here, which is if you have less capable components, traditionally you get errors. But in this case, if you have less capable components, you get a less capable design. I'm going to show you exactly what I mean with an example. So I discussed this a bit. I think it's worth repeating. Static if is an incredibly powerful tool. And actually, it's even more so than static looping. But static looping does the same thing for for several iterations, for each method in a class or whatever. But static if is the fork. Static for is like more of static if, really, right? So there are 3 designs that have been realized that are inspectable. One would be STD experimental allocator. It implements like really any allocator you please within 12,000 lines of code. There's a lot of structural work in there. There's a lot of algorithmic work in there. But when you sum it up, it goes to this much code, and that includes documentation and unit tests and everything. By comparison, JMalloc the sort of the industry leader in memory allocators, implements exactly one allocator in 45,000 lines of code. Mind you, these are hardly comparable. JMalloc is, it is written in C, which is a more verbose language, and it uses none of these generative techniques. And it's solid. It's an allocator that has so much detail going into it. It's used by a lot of the industry. But I like the trend. I like the fact that I can have any allocator I want, including JMalloc, within a fraction of the source code. Collections, you're going to see Edward's talk later today. And we're going to discuss right now checked-int, which is a new package in STD experimental. Now, you know what they say. If it happens once, it's a bug. If it happens twice, it's a feature. If it happens 3 times, it's a new programming paradigm, right? So we go with 3, right? So checked-int. Well, at this point, you can go to sleep and take a nap. This is a boring topic. Actually, pretty much what happens with checked integrals is we want to, make sure we don't make these overflows and stuff. And we have a number of operations that may lose information. We may have division by 0. We have this weird problem by which there's one special negative number of which negation is also negative. Thank you very much, two's complement representation. But it's a great representation because it has only 1 0. It's good for many other things. But, we have this one, this one pesky number, the smallest signed integral. If you take the minus of that, it's also the smallest signed integral. So it's kind of a bummer. And then we have these odd comparisons, such as -1 is the same as u in dot max. Very large positive number is the same as a -1. Then we have things like -1 is greater than 2 unsigned because it gets converted to unsigned. So there are good reasons for these oddities, but of course you want to avoid them from, you want to prevent them from happening. But that's pretty much it. It kind of stops there. So we have a number of possible designs here, the simplest being, let's design them out of the language, right? So let's define the language in such a way that this doesn't occur. They come at a runtime cost, so in a way they're not interesting to a systems programming language. But such languages do exist, and they do work. It's a great thing for certain domains. You integrate within the programming language. You do away with fixed size. You have like large integers, whatever. And I remember like OCaml has an interesting optimization. They reserve a special integer. I think it's is the most negative integer. They reserve one special integer to mean, oh, that's actually a kind of an unbounded number, but the rest of the integers are 31 bits. So that would be one. Another would be have the program insert tests appropriately for an appropriate definition of appropriately. Who's ever tried that? A couple of us. I tried it. And it triples the size of any function that does anything. It's ridiculous. You look at it and it's like, oh my God, I got to check this. And 2 lines later, it's like, oh my God, I got to try this too. And I check that too. And check that. It's crazy. It's completely insane. And it leads to a function you don't know what the function does anymore. If you didn't know before, this is not going to help. Okay? So it's ridiculous. So I don't think this is really workable. And inevitably, we're going to forget a few places, as it always happens, etc. So going with other possible designs, we can say, oh, let's designate a checked integral type and use the nice operator overloading capabilities within the language to make that work. So, okay, so then all you need is to replace int with checked int, and it all kind of occurs automatically. Very nice. So now, let's say we go for the second design, and there are a number of challenges. What exactly do you check? Are there overflows? Maybe you care about overflows, but not about truncations. Maybe you care about overflows and truncations, but not comparisons. And by the way, if you ever see this particular -int.min, I want you to abort the program immediately. That kind of stuff. And any of these is, yeah, I can do it. It's 5 lines of code. You can just do it. It's any particular behavior. The problem comes when you try to do it generically, right? So this is the real problem here. It's not difficult to implement a given behavior. What's difficult is to define a library that implements any behavior, including behaviors that you haven't envisioned yet. Right? That's why we have these large libraries that come with propositions like, actually, I think I'm sort of quoting from memory a forum post. You mean I need to use this ridiculously large library that comes with a huge manual because I want to check a few comparisons? So the problem here is that the scaffolding necessary for genericity, it scales poorly with the number of behaviors I want to support, with flexibility. So if I want any one particular checked integer design, I can do it. If I want to support any reasonable checked integer design, then the size of the proposition becomes like real large, actually exponentially large almost. So there's something here, right? So I did some research into what's there, and I found the following packages. Mozilla has a checked-in for C++, which is small, but it does almost nothing. It stores a Boolean with the operation, and I think that it's very slow. I think they found a guy and told the guy, please write the slowest addition you can possibly master. Don't put a loop because it's too obvious, but make it as slow as you can. And that's the requirement. That's the number one requirement. And by the way, make it big too. I want the integers to be twice as big. If it's 32, 64, no, 128. 64 is no, it's yesterday's news. We want the big thing with an integer and a Boolean next to it, which takes another word. So it's terrible. And oh, by the way, we want zero configurability. We want to be able to do nothing with this. All we want to do is give the guy a Boolean to say, some operations failed at some time. That's all. That's the maximum you're allowed to implement, right? So of course it came in 800 lines of code. So then we have the opposite end of the spectrum, which is the Death Star of checked integers, Microsoft's SafeInt. It's 7,000 lines of code. There's probably 30,000 lines of documentation. It's like an MSDN thing. You gotta have the DVDs, otherwise, it's a huge proposition. It's officially supported. I don't know. I think Steve Ballmer worked on it for a while. It's a huge thing. Okay, it was a major project at Microsoft. And then we have Safe Numerics, which is a Boost library by Robert Ramey. Actually, if you Google for his name in ACCU, he has a great article about why checked integers are good. It's also a hefty proposition because it not only has 5,000 lines of code, but also it requires a bunch of advanced Boost libraries such as MPL and whatnot. So it's kind of a heavy proposition. And we have our own, definitely not, last but definitely not least, we have our own checked-in for D by T.S. Bachman. I'm sure you're familiar with his name from the forums and his contributions on GitHub, which is a policy-based design, which is fairly compact and nice in 5,000 lines of code. And that was actually my main baseline, my starting point for saying, you know what, this can be done smaller and better and more general. So looking at the size that I'm proposing here, we're looking at 3,000 lines of code, unit tests, and documentation, distributed almost evenly between the mainline code, which is 1,200 lines, documentation, which is 900 lines, and unit tests, which are completely covering the design, 900 lines. And The generality of this library is way surpassing all of the above. And the speed is comparable to the, what you would do if you hand inserted all the checks yourself. The overall design of checked-int, just getting a bit into details here. I'm going to have a shell with hooks kind of approach. You have a shell, which is your table for assembling things, and then you have one hook, which takes care of everything. So you're going to have a checked, and that's my integral type T, and the hook is going to be by default abort, and we have a constraint on this thing, which I'm going to get back to, which means this type must be an integral. And we have the payload as a private data member, and we have the hook as another data member. What is the first thing that raises a brow here? Yes, Joe.
Well, you made it big.
Yeah, I made it big. Literally, not figuratively, right? I made it big. Not good. So most hooks are actually stateless. So if they're stateless, no problem, we know what to do. Static if state size is greater than 0, I'm going to insert the hook as a regular member. Otherwise, I'm going to alias the type to the same name. What is the consequence? Yeah, no size penalty, but the nice thing is syntactic. If I write hook.something, in the first case it's member.something, in the other case it's type.something, they both work the same. Right? That's pretty awesome. So we got rid of the, making it big thing, so much about that fear of success. So now we have the default. Actually, we want to configure the default initialization value just because certain hooks would want to do that. For example, a certain hook may want to allocate a special value for the integral to say, you know what, this is not a number thing, like in floating point numbers, right? This is not a number, uninitialized, non-existing, not valid. So they want to initialize the integer to that. In that case, I'm going to do a query, static if has member hook default value, then I'm going to say private T payload equals hook default value of T. Otherwise, there's no particular initialization. So all of a sudden, in 4 lines, we're already kind of somewhere, which is interesting, remarkable. Like we have a way for the hook to define its own initialization, if so pleases, and we have a hook that may or may not occupy space depending on whether it needs or not any space. So now we have the shell, which is the checked-in type, which factors all commonalities, handles all qualifiers, const immutable, what have you, drives the hooks, integrate with the type system, all the conversions and the casts and everything, and mediates the composition of different hooks. I'm going to get back to that in a minute. And this is particular for checked-in. It's not needed for all designs. For example, the allocators design does not have any shell. It's just the allocators, which compose naturally. So, all right, I talked a bit about this graceful degradation thing. And the simplest thing you can do with checked is say checked of int, comma, void, which is a great baseline test, a very good dry run of checked int. Because it goes the following way. If you put a hook that doesn't do absolutely anything, has no state whatsoever, knows how to do nothing, then what do you get? Int, right? You get whatever int does, this should do. Because there's a degradation of features offered in the sense that if you have a check type, but if you have no checks, it's int, right? So now this guy with void behaves like vanilla int. And actually, this is a unit test. It's a thing because it's a dry run through the whole design. And it's very useful for make sure your approach is sound. Control design through versioning, maybe you alias some type to void or something else. During release, void is appropriate. And you get to cover a larger design space by having this particular corner case taken care of. So that's a graceful degradation thing. Now let me give you an example of how you implement some arbitrary operator. I chose increment and decrement. They go together. And it's not really that complicated. And again, it's all static ifs, of course, because they're good. I told you I want a diet of static if in my life. They're like the fiber of design. Okay? The good fiber, not the bad fiber, okay? Is there bad fiber? I forgot. There's soluble fiber and non-soluble fiber. You know, look it up. I have no idea. So again, I'm saying a lot of ignorant things right now. So if the hook decides to hook this particular operator, then I'm going to defer to it. So my first decision in the design is maybe the hook wants to completely intercept this operation. I'm going to give priority to the hook. Otherwise, maybe the hook wants to detect on overflow. So it implements this particular primitive on overflow, in which case I'm going to say, well, let me look at the operator. Is it plus plus? If it's plus plus, I'm at the limit. Then I'm going to call on overflow, passing it the appropriate information. And otherwise, I'm going to do the unchecked operation plus plus payload. If the hook is not interested, you know, plus plus payload is going to be the only line of code generated if the hook is void, right? Because it doesn't have any members. So then else, then operator is minus minus, and then we go again with the test. If payload is the same as minimum that payload, then I'm going to call on overflow again with the appropriate information. Otherwise, I'm simply going to decrement payload, and otherwise I'm going to use mixin because that's what the cool kids do, right? I'm going to use mixin here because it could be plus plus or minus minus. I'm just going to mix in the string of plus plus or minus minus with the payload, and I got it. Make sense? Yes, thank you. Great. And that concludes a simple implementation of one of the shell functions. It's just the increment and decrement, and depending on what the hook knows and wants to do, it's going to have a different implementation. So by the way, actually, this is not one implementation. This is how many implementations? We count by static ifs, right? 1, 2, 3, 4, 5 implementations in one. Oh, sorry, 10, because we have like this case too. So we have a bunch of implementation flowing through this particular compact piece of code. All right, so after kind of you sit down and you actually go and finish the design, you get to the conclusion that you need only a few optional hooks, which are the following. You need default value minimum and maximum, because a hook may want to redefine minimum and maximum. Any ideas on what those might be? Who would want to intercept int min and int max? Sorry? Bounded integers would want to implement that. Actually, this is interesting. I didn't get that design to support that yet. But there's a simpler case, which is integers with nan. Because nan would be like the most negative integer. It's a reserved value. So min is got to be like just the next one, right? Yes?
So for some of our integers, since we cannot spare the extra memory, we also keep a little bit of bit fields at the higher bits of the integers, and then we have similar code checking that
so you have like
we aren't overflowing into these areas.
That's awesome. I can tell you're doing efficient stuff because like all of this bit manipulation is like huge in efficient programs. That's great. What other hooks we have there? Intercept and override. We have hook, op cast. It's called whenever you want to cast things. Hook, op equals, comparison, unary operators, binary write operators, and op assign, which is plus equals, etc. So if the hook defines any or all of or a subset of these, they're going to be called appropriately by the shell, right? And then we have the simpler way to look at it. I just want to handle the event, in which case the computation has gone already wrong, which is on bad cast, a cast that would be losing data. On overflow, which would mean whenever you overflow a multiplication, for example, or an addition, on lower bound or on upper bound. So clearly, you either implement some of the hooks here or implement some of these, but it doesn't make sense to, for example, implement hook, OP binary, and also implement like on overflow. Because the hook is going to be called, not the event handler. Right? It doesn't make sense to do both. You either hook it all together or you implement the event handler, right? So there are not a lot, and they're all optional. So I defined a number of hooks. One is abort, which simply look, whenever something fishy is going on, it aborts the program with a message. The message is informative, you can't do this, there's an integer that's too large and whatever. One is throw, that does pretty much the same things, except it throws an exception instead of aborting the whole thing. We have warn, which just continues execution with a predefined int semantics, but it just logs a message to standard error, right? We have an interesting one, which is proper compare, which actually fixes the wrong comparisons. You know how to fix comparisons of signed and unsigned types, right? Thank you.
You use the bigger size integer.
What if it's long and unsigned long?
You use sent and usent.
What if it's sent and you sent?
You use some wide int library.
No, that's not the answer. So, Robert?
Yeah, if you first check if the signed one is negative.
Yeah, you do two comparisons.
Yeah,
Thank you.
and then
So you do two comparisons. If you compare an int with an unsigned int, for equality, for example, the first thing you do is the int less than 0? And if it is less than 0, it's clearly going to be less than any unsigned, so you're done. And otherwise, you're going to cast to unsigned, and you're going to continue the comparison. So it's double the cost. So it's not zero cost, but it's doing the right thing. So there's little price you can put on correctness. So that's what proper compare does. It just intercepts these operations. It does them right. With nan, it reserves that not a number value. And interesting, we have saturate, which whenever it overflows, it kind of stays at the maximum, respectively minimum values, right? These are all interesting behaviors. And most interestingly, you get to define your own hooks. And just to give you an idea on how difficult that is, not like defining your own, your own complicated range class or whatever. It's a simple proposition. We're looking at 50 lines on average for these policies here that we're talking about. For example, let me implement one of these hooks right now, which is no pesky comparisons. It's going to hook OPCMP, so that's comparison for inequality, and whenever that happens, it's going to actually test whether that's the situation that I'm looking at, and it's going to assert 0 with a message. And now I have an integer that avoids the pesky comparisons. But wait, there's more. How about I don't want those to compile even? It's not that I want them to fail at runtime. I want, whenever I compare something signed with something unsigned, I want the thing to not work. How do you do it? Yes? Static assert. But what do I put in static assert? Well, I disable that statically. Look at this. I have static if condition. I'm reaching the situation. Then static assert 0, and otherwise I'm going to just return the right comparison. So I actually get to define hooks to refuse compilation of certain cases. So the space cover here is huge. It's not that I define hooks that do things at runtime. I define hooks that guide what I can do at compile time. Speaking of which, let's discuss a bit composition. I have the youngest member of the community entering right now. Awesome. Must be 5 and 2. OK, awesome. So let's discuss composition a bit. I'm sure they'll have a lot of fun with that.
They're here for the new mentorship program.
Yes,
Andrei.
the whole mentorship and internship program. Yes, kids, you're in the right place. So there's no exponential without composition. Is that a famous quote? It just became, right? So let's talk about composition, because composition is where you get the big things from small things quickly, right? Composition explodes, it's all of this combinatorial behavior, right? So composition, it goes the following way. Traditionally, check works with integrals, but now I figured check needs to self-reflexible compose with itself. you must be able to build a checked int on top of another checked int. And that's how you multiply whatever the first guy does with whatever the second guy does. So that's the secret sauce to getting a lot of behaviors with only that 1,000 lines of code. Okay? So that brings up the unique opportunity. So check works on top of itself. Wow, okay. As Scott said yesterday, the pit of success. It means, oh, let me write this, let me try this, see if it works. Oh, it actually does work. Amazing. So some combinations just work. For example, consider checked, checked in, proper compare. So we get something that does the comparisons the right way at a small cost, and everything else, whenever overflow, whatever is going to abort the program. And I didn't need to sit down and write either of those again from scratch because they're just assembled and that's it. And the second example that works very nice is I want to have an integer with nan, but also fixed comparisons. Right? However, so as I kind of experimented with this for a bit, so I kind of played with it for a while, some combinations don't work. So I was bound, for example, does it make sense to hook something that aborts with something that throws? No, because they're both suicidal, right? There's no, oh, I'm throwing, and by the way, right after that, I'm aborting the application, right? Or I'm aborting the application, but you should know that, if that abort didn't work out, I'm going to throw as well, right? It doesn't work that way. It doesn't make sense. So abort, throw, and warn can't be built properly with each other. Warn actually is doesn't make sense because you warn and then you get abort and you get the same message twice. The reason for the error. So it doesn't make sense. It also doesn't make sense to abort or throw before proper compare with nanosaturate. So these combinations just don't work out. These compositions are. We have a few compositions that are either inefficient or ambiguous. They run the same operation twice, or they're just ambiguous, and it's unclear what you want. For example, warn and fixed comparisons, you want to hook the same thing twice. It doesn't make much sense. You could establish a policy, but any policy would be rigid. So you don't want to do that. Or you want to fix comparison and then warn for all others. So there are a number of combinations that are just not working out. You just see through the code and look at it. You're trying the same operation twice, so it's just ambiguous. It's unclear what it should be doing. It's not cool. So for these, I came with, so I actually lost sleep over this, a couple of nights, and I was thinking, there's got to be a better way. And there is. It turns out you can compose these easily by defining new hooks that, assemble by hand the molecules, right? You assemble the molecules by hand. It's the buffet of hooks. You say, you know what, for this particular hook I want, whenever there's a bad cast, I don't like that. I don't care for that, abort, right? But, if I have a cast that would go from, for example, from int to short, if it doesn't fit, I want the maximum short. If the integer is greater than the short, I want the maximum short. You saturate that. Fine. The same goes for plus and minus. And then on overflow, I want to saturate. On comparison, I want to abort. And on comparison for inequality, I also want to abort. So we define this simple hook by means of assembling existing hooks by hand, quite literally by hand. It's just a very pleasant assembly process because it's only 5 lines. It's just as many as you care to implement, and you pick and choose, and this just works, which is awesome. So I advise you to take a look at that. I think it's a great opportunity. And with this, I'm kind of getting to the point where there's so much opportunity there. There's so many things to do. As I was saying yesterday, there's a lot of methodologies and stuff, and ways of doing things, and new stuff coming down the pipe, which is disallowing you to do things. It's like these laws. You shouldn't do that. You shouldn't do that, restrictions. But I want to do more things. More things are better with less code, right? So I get to do a lot of things with a lot less code by means of design by introspection. And this is where I think the killer application is. I think this is like, I really believe like that there's this famous saying by Tolstoy who said, all happy families are happy in the same way. All unhappy families are unhappy, each in their own way, right? I think all people who like the D language, they like it for introspection, for this stuff. I don't think there's anyone, oh, they do classes like really like Java. This is awesome. I like that. It's not like that. This is what everybody's like, oh, and at that point I inserted a static if and it was amazing. That's what happens. Nobody says, I wrote a struct and it was amazing. Nobody says that. I figured everybody who likes the D language likes it for this one reason. Everything that makes design by introspection up. So, you get to assemble designs with plastic, adaptable components that understand each other and talk to each other by means of introspection. You have this notion of exponentially covering optional interfaces. You have this notion of automatic or semi-automatic composition by hand. You cover with linear code a bunch of design space, and you degrade gracefully when there's insufficient interfaces. You've been great. Thank you very much. Thank you.
We have time for just a couple questions.
One comment, since you say destructionize, I was going to say that you have the exponential blow up in the introspection templates, and that would make stuff really, really slow because you're covering exponential stuff, but you're also increasing your compile time exponentially. But during the talk, I essentially know now how to fix that use case, and it will be linear in a couple of weeks. That's just what I want to say.
I have to disagree here. I think we're good as we are. Of course, better is better, but only the realized path are, cost you anything. It's
no,
not.
we don't. Normally, you have to pay for the introspection itself in templates, but I realized that this is a special case because all we use in introspection templates are traits or is expressions, and if we detect that only those are used, we can do a special thing in the template instantiation, and it's going to be super fast. So you don't have to change your code, but introspection, it's viable now. So.
Okay, we should take this offline, but basically I disagree. I don't think that's the case. I think faster is better, but I don't think that's a fundamental issue. Yes. Yes.
Is there a way to list all the hooks? So I was thinking that, for instance, if you add another hook to the checked-in saying, don't know, on division by 2, for instance, and I sort of didn't see the pull request that do that, and my class that throws whatever doesn't know about the hook. I mean, it still compiles, but as you said, it sort of doesn't do anything. Is there a way to list all the hooks and check that as basically a person that implements that? Because I sort of want to know that I got all the hooks.
Right. You want to do fewer things. I think checks are entirely appropriate. For example, when you get the hook, you want to list it and say, does this hook implement only the meaningful operations? Or does this hook implement all of the operations? So definitely this would be a good companion to checked int. It would be like, check the checked int kind of thing. Check this hook that it implements all of the hooks. Definitely, yeah, such tests for maximality would be appropriate.
Yeah, or just have like a static array of all the hooks in the checked int, which I can introspect from the implementation.
Right. That would be the other side of the introspection, which you like, let me define what hooks I'm supporting here. Yes, thank you. That's a great idea.
We have time for one last one here.
Yes, please.
I'm about composition. you have examples that, okay, this composition is meaningful, but this composition is not meaningful or nonsensible. Is it way to design by introspection to verify and say the user that your components is not
Can you
composable?
verify? Yeah, actually you can. But I'm really impressed that everybody says, oh wait, you're doing too many things, some of which don't make sense. So let's do fewer things. So philosophically, I'm opposed to this. But whenever a build checked on itself, essentially you get to introspect. You can say, well, are these two hooks both implementing, do they want to both implement on overflow? In that case, you can reject the design statically. You can say, you can't hook the same thing twice. It doesn't make sense. So there is, on the assembly, the shell, there is opportunity for mediation of conflicting hooks. And you can either make decisions. You can say, oh, if you both implement the hooks, I don't know, take the left one, take the right one, take one of them. Try both or whatever. Or you can say, this design is not valid by our... I shouldn't do follow-ups, but yes, please. Dylan is going to kill me.
Just one thought to resemble what you say, that we have conflicting hooks or something like that. It just recall me the categorical algebra in mathematics and categorical approach in programming, that you just define category, how you can combine these hooks or how you cannot, and you just, after that, you have all sequences of this.
There's a little algebra there. For example, just off the cuff, I'm thinking, if you have two hooks on overflow, the first one you execute cannot be throw. It must be no throw. So you get a chance to execute the second one, right? That kind of stuff. So there might be a little algebra for composition. I didn't find it. So I think it's better to just assemble things by hand, give the people the clear opportunity to do it by hand. With this, I think we're done here. Thanks again very much. You've been great. Thank you.
Thank you, Andrei.
Thank you.
So I actually want you to stay on stage for a minute.
All right.
We didn't talk at all really about Sociomantic, and someone did ask, what does Sociomantic do with D? Maybe you'll hear a little bit about that from Hatem during the lightning talks. But one thing Sociomantic really does is contributes a lot to the D language by creating new keywords, one of which was the homeboy keyword. I'm not sure if, maybe, okay, there's some laughter. Some people either know of that or just find the word homeboy funny to begin with. So for those of you that don't know, we have a tradition at Sociomantic of putting people on T-shirts without asking their permission. Right, Andrei remembers. So, okay, so I think it was, I don't know.
What's underneath that?
In the first days that we knew Sociomantic was going to survive as a company, we took Walter's face and put it on a shirt, and it said, Walter Bright is my homeboy. And the whole company was wearing this shirt. And at events, and people had no idea what was going on. Who's Walter Bright? And we were like, yeah, exactly, my homeboy. And then we thought, we wanted to honor the other homeboys and homegirls, all the home people in the D community. So we put Andrei's face on a shirt last year. Andrei is my homeboy too. It's a very young, beautiful version of Andrei.
What do you imply there?
So this year, we were trying to think, like, who's the next homeboy, right? And we were going through, like, all the usual suspects. We were going through all the, like, most active GitHub accounts. And we just thought, like, no matter who we put on a shirt, we'll be leaving someone else out. And so, I mean, it just became obvious.
We got the zombie attack going right here.
It just became obvious that the next homeboy had to be someone whose name is not so relevant. You need some help there? D community tourist.
Voldemort.
He wants a photobomb. He wants a photobomb. You can't say that name. It's legally improper. Yeah. So this year we decided to put the he who should not be named is my homeboy, and then scratch that is my type. Woo! So.
That's a pretty awesome idea.
Hopefully, like, everybody understands that joke. You should understand that joke more than I do. But anyways, we made some shirts. We didn't want to continue honoring individuals in the D community. We wanted to honor the entire community. Yes, thank you for your presence here, young man.
Thank you. For Mr. Voldemort. Oops.
So when we go to the break, yeah, you can't say the name,
you
right?
Can't say the name.
Not just because of the joke, But you can't say the name for legal reasons. We'll get sued by Warner Brothers or whoever owns this franchise. So when you go to the break, we have some bonus T-shirts for you out there. Please grab one. And we'll be working with Andrei and with Walter and the D Foundation to hopefully get the past Homeboy shirts available for purchase to support the D Foundation in the coming months.
Awesome.
So.
Thank you very much.
Yeah.
Thank you.
All right. So with that, I relieve you all to your break. Come back in about 5 minutes for the second speaker of the day.